Hello everybody and welcome back. Today we're going to be talking about recrystallization. So without any further ado, let's get started. Objectives and goals for recrystallization. So oftentimes when I create a lecture for you, I include a slide that has objectives and goals. So at the end of this presentation, by the time you're done reviewing the video content, which I very much so encourage you to do, before your assessment, you should be able to summarize the key ideas that I have listed for you in the objectives and the goals sections for all of our PowerPoint presentations. And particularly here, there's a few points that we should keep in mind as we're going through the recrystallization procedure. And that is recrystallization introduction, but specifically, how is recrystallization applied to organic chemistry? The requirements of solvents that we choose for recrystallization of certain compounds. And this is particularly why it was important for us to start our discussion with the topic of solubility, because solubility is so incredibly important when we try to determine, is this liquid solvent polar, nonpolar, or somewhere in the middle? And what type of solvent do we actually need to recrystallize our specific compound? So keep in mind the 10 rules that Pavia stated for solvent selection for polar versus nonpolar compounds. If you don't remember, please refer back to chapter 1 that's listed in the solubility folder. Volatility as it pertains to recrystallization, and why in particular that is important. Recrystallization of a solid, and basically the in and outs of how you would go about doing it, and the different troubleshooting that you might have to do in order to successfully recrystallize a solid. And finally, we're going to talk about the principle of decolorization and how that actually helps us if in fact we should recrystallize a compound and it should still have impurities trapped inside of it. And we will discuss what an impurity is also. So, without any further ado, let's move forward. Introduction. Recrystallization is the process by which you take a solid solute, you dissolve that solute, or you solubilize it in a particular solvent. The solute is thereby purified, and then it is crystallized again into a new crystal that is of the same chemical makeup as it originally was. So this is important for us to remember. Recrystallization is not an organic synthesis reaction, meaning what you start with, the original solute, should be the exact same thing that you end up with at the end. The only difference is that the impurities or the dirty stuff that's inside the crystal should be removed, and therefore your crystal will go from dirty to pure, or in scientific terms, crude to pure. So recrystallization, the whole idea and the objective is that it is a purification technique. Consider sulfanillamide. If you Google sulfanillamide really quick, don't really concern yourself too much with the chemistry just yet. But if you Google it, you might find that sulfanillamide had a lot of practical uses in the medical field. And actually, sulfanillamide is a derivative of an antibiotic. It was used in World War II as a first-line treatment for soldiers who had certain types of infections. And by that means, you can't take an antibiotic and administer it to somebody and just give it to them and hope that they're okay. That antibiotic goes through a lot of phase trials and blah, blah, blah before it's approved to be issued into the pharmaceutical world. And in order for it to be approved, it has to has to meet certain quality control standards, meaning that it can't have a bunch of other junk inside of it that we don't know what it is. It has to be purified. And we're speaking of sulfanillamide because that is your, quote, unknown for this lab. We're actually going to recrystallize sulfanillamide. So the whole point is not just to take it and turn it into a crystal, but rather the whole point is to take this impure or crude sulfanillamide and to recrystallize it into something that actually is pure. And it's important to remember that because if you are in a lab where you're given an unknown, which could happen in this course, say there's 3 students and each student is given compound A and compound B and compound C, and say one is sulfanillamide, one is urea, and one is benzophenone. You know, sulfanillamide and benzophenone kind of look similar to the end product after they're recrystallized, meaning what you had at the beginning kind of looks like what you get at the end. Urea, though, especially our urea, is actually in pellet form. So you have these circular little pellets, and they might have little blemishes or little black marks that might symbolize that they're impure and there's something else in them. And then when you go to recrystallize them, they actually elongate. And this is not a picture of what that is, but I am using this picture just to kind of show you what recrystallization might look like from the beginning, what would be part B, to the end, what would in this figure would be part A. So when you're done, a student might look at the crystal before and after and say, oh, look, a really cool crystal actually looks like a crystal. It's long, it's geometric, it's shiny, and that's all wonderful. But that wasn't what we were trying to do. We weren't trying to grow crystals. We can actually do that. You take 36% copper sulfate, you dissolve it in water, and hang a little string on the middle with a little weight. You leave it in there for like maybe a month or so. You come back and there's this beautiful blue crystal of copper sulfate that has built a scaffold around that string. And that's really cool. But that is crystallization. What we are doing is recrystallization. And that is the difference in these terminologies. Recrystallization is taking a crystal that's crude and recrystallizing it with the intent of removing impurities for the sake of purification. Crystallization is just taking a solute, dissolving it in a solvent, and then crystallizing it again with no impurity being excluded. That is what crystallization is. And the third is precipitation, which can actually happen in this course if you take a solution and you oversaturate it. Rather than getting crystals at the bottom, what you'll get is a very fine precipitate. If you diverge from the procedure, and you should do what's referred to as an ice shock, which we'll talk about a little bit more, you will actually force the crystals to precipitate down. Rather than going slow and steady and growing your crystal lattice over time, you'll cause an ice shock for the seeding crystals lattice to encapsulate impurities and trap them back. In which case, if you attempt to recrystallize something and you ice shock it, you actually trap the impurities right back where they were, and in fact, you've actually now have an impure crystal again. So, recrystallization, crystallization, precipitation are 3 very different things, and what we're focused on is recrystallization. And again, solvents can be 1 or more compounds. Consider water, very high on the polarity index, very, very polar. Consider hexane. Now consider that I have a crystal that I think might be, it might have polar and nonpolar compounds. You might think, oh, well, I can combine these 2 and make a solvent that has the best recrystallization properties of both. But if you thought a little bit quicker, or if you thought a little bit more cleverly, you might find something wrong with that interpretation of solvent mixing or preparation. Take a moment to pause this video and think why mixing ethanol and hexane to recrystallize a solute that has polar and nonpolar compounds is probably not the best idea. Pause this video and think about it. Write it down in your notebook, and then I'll give you the answer when you come back. Okay, so by now you should have done that small little assignment. And if you thought that by mixing ethanol and hexane, that would be a good representation of a solvent that has both polar and nonpolar properties, then you would be correct. However, we remember that polar and nonpolar compounds, when they are mixed together in liquid form, they are immiscible. So these two solutions would not mix together. And when it comes to solubility, if sulfanillamide, or just say an unknown, is added that has a little bit more polar properties as opposed to nonpolar properties, it may solubilize in one layer much better than the other layer, because the other layer is not really efficient for solubilizing perhaps maybe, say, 75% of this crystal that's polar, whereas the rest, 25%, might solubilize in a nonpolar solvent. So it depends on what you're looking for. The best thing to do when you have a solute that needs to be recrystallized in a solvent that is polar and nonpolar, you should actually take a solvent that is already somewhere in the middle on the polarity index. I'm going to show you my own little polarity index so that you can kind of conceptualize, well, if I have a polar compound and I want to solubilize it in a polar solvent, maybe I should choose one of these. This guide is going to help you, and we'll talk about it a little bit more. But for now, just remember, solvents may be one or more chemical compounds, or they may be just one that is somewhere in the middle of the polarity index. There's strict selection factors for solvents, and we already talked about some of the ones that are really important. Polar versus nonpolar compounds in comparison to your unknown. Now, if we gave you an unknown in a lab, we would have to give you a solvent that's going to recrystallize it just fine. We wouldn't want you to be picking solvents, especially in this course, on your own, unless you're specifically told to. If you're not told that you do not need to test the solubility of your compound, just use this, perhaps 95% ethanol, then you can rest assured that that's going to solubilize your compound. It's not to say that it's totally polar and totally nonpolar, blah, blah, blah. It's only to say that this is going to work for your compound. If you're told, however, that you need to figure out which is the best solubility solvent for this particular crystal, then you would need to do basically your own version of the solubility test that we already did on week 1 and test each of the solutes given varying different solvents and keep going until you find one that works. That's how you would select an appropriate solvent if you weren't already told which one to use. And the crystal, being recrystallized, forms a lattice that is very rapid. That is what is called non-selective. If you take a crystal and you try to recrystallize it and you do it really quickly, it recrystallizes in what is known as non-selective recrystallization, and that process does not include purification. For example, if I take a crystal and it's in solution, and then rather than let it seed or to grow at room temperature, I shock it in an ice bath, it takes all of the crystal seeds or the lattices and it tracks them together really quick. Whereas over time, the scaffold folds very, very smoothly, very, very slowly, and it can actually exclude the impurities from the lattice that it was already trapped in. So we never want to perform or facilitate a non-selective recrystallize. We never want to take a crystal and put it in a condition where it's too cold that's going to force it to recrystallize in a quicker fashion than it would at standard room temperature. So when a crystal lattice grows slowly and when it is able to reform its stable configuration, it will form the exact same crystal over again, but it will do it very slowly in what's known as selective recrystallization and therefore exclude impurities. And therefore the crystal that you get will be identical to the chemical makeup that it started by, but it will no longer have the impurities that are going to actually, in the end, affect not only the identity and not only the spectra, but it would also affect the melting point too. And next week we are going to talk about melting point and mixed melting point and how these two labs go hand in hand with one another. As we continue our introduction, I just wanted to kind of give you a look at one particular crystal that's very, very common, and that just happens to be a diamond. And for those of you who are fond of precious stones or gems, diamonds are very, very popular. If you remember, there was, I think in the 50s, a commercial that's famous slogan was "Diamonds are a girl's best friend." That was Tiffany's. That is how Tiffany's actually got their start, with that slogan, by making a gem, or in this case a diamond, something precious and desirable, and therefore they put a high dollar amount on a gem. But if you know what a diamond is, it is just carbon, and carbon is abundant. You take carbon, you put it in a pressure cooker, you can make your own diamond. And if you ever have a loved one who passes away, there are companies who will take the ashes of that loved one and they will turn it into a diamond, and you can wear it as a tribute to your loved one. So diamonds are not as rare as people think they are. Naturally harvested diamonds are, but you can grow them in the lab and they're just as beautiful and they're just as high grade. And just as there are different grades of diamonds, there's also different types. And if you look all the way to the left, you're looking at a black diamond. Black diamonds, for some people, are very rare, and they are very prized, and they're very expensive. When in reality, I'll tell you a funny story just to make you laugh. I knew someone, this young man, who had proposed, or had actually thought to propose, to his girlfriend back then. And as he was just talking about the idea to see if she was interested in marriage or not, he told me that she said, "I would never accept an engagement proposal from someone who did not give me a black diamond, because those are the most rare diamonds that there are, and they're most expensive. And he must really love me if he gives me a black diamond." I remembered that story because it was just so far-fetched. When in reality, a black diamond is nothing but a dirty diamond. All that black in there are impurities. Those diamonds are almost in their natural state, and they are made that way, or they're harvested that way for that black pigmentation. But if it was more pure, it would actually look like a white diamond. So you talk about purity and you talk about impurities. I hope that this example at least helps you remember, hey, if you have something that's clear and colorless, it might not have impurities. It's not to say that it doesn't. It's just to say, at least in this lab, it probably doesn't. Purities normally go hand in hand with pigmentation. And in the Sulfanillamide experiment, you're going to see that we give you a specific vial or ampule with sulfanillamide, and it's going to be bright yellow. And that is not, if you actually Google, again, sulfanillamide, which you always should do, you should always Google this stuff, you would see that sulfanillamide is white and colorless. Actually, I shouldn't say that. It's clear and white in pigmentation. It's not clear and colorless like water would be, per se. It has like a white hue to it, but it's certainly not bright yellow. So if you're looking at something and it's bright yellow, you say, oh yeah, that's probably a contamination. Unless that crystal by nature has a bright yellow color, and some do. And that's important to remember. You should write that down. Some crystals actually do have color. They actually do have pigment. And because they have pigment, for example, copper sulfate. Copper sulfate's blue. If we were to recrystallize copper sulfate because we thought maybe it was impure, yeah, you would get the impurities out. But in the end, in the solution, you would actually have a faintly blue solution because some of the pure copper sulfate just happened to go into the solvent and was taken out with the crystals. So at the end, yes, you're purifying a compound. Yes, that compound may not have impurities anymore, and yes, it can still retain its original color. The place to make sure that a crystal should have this specific color, whether it be purple or pink or blue or green or whatever it is, you should check the CRC. Bromocresol green happens to be green. Copper sulfate happens to be blue. There are different crystals that are different colors. So if you recrystallize something and it doesn't come back clear and colorless, that doesn't mean you didn't do anything wrong. It could just mean that the chemical makeup of that specific compound just so happens to have that pigment that's still there. Okay? Requirements for solvents. Solvents for recrystallization should not react with the compound. This is not a chemical reaction. If your solvent reacts with your solute and it makes something new, you didn't purify it. You synthesize something. So the solvent cannot react with the solute. Otherwise, it's going to be something different by the time you get it back. Remember, the goal is to take this compound that's dirty, crude, recrystallize it to take out the dirty or crude impurities, and then to crystallize it again, or recrystallize it, and therefore take that new crystal that is exact same chemical makeup, but is just now pure. So, a solvent must also be somewhat volatile. And with specifically sulfanillamide, you're going to use 95% ethanol and 5% water. And that's a pretty polar solvent, but it's also one that's very volatile. You don't want your solvent to sit on your crystal. You don't want it to just go stagnant there, because if it does, you are not going to be able to take the solvent out. And at the end, you want to dry the crystal because you need to get a melting point, and you can't get a melting point on a wet crystal. So solvents are best volatile, but not so volatile that they vaporize away your solute. And that can happen with some of the unknowns that were given in the past before I got here. The solutes on their own were a little volatile. And then the 95% ethanol was also very volatile. And at the end, some students would come back and they wouldn't dry their crystals enough. They would come back at the time of their practicum, their final, and they would have nothing. Like, oh my God, what are we gonna do? Well, they saturated their solute in a volatile solvent and it vaporized away over a week before they came back. So, yes, the solvent should be volatile. No, it should not be so volatile that it ruins your results. Okay? And a solvent should have a high solvency for the desired substance at high temperatures and low solvency for a substance at low temperatures, meaning at high temperature, that solvent should dissolve the solute. And at low temperature, it should not dissolve. And that is a very, very important trait that you should write down to remember that a solvent for recrystallization should have. A solvent, if you take a solvent and you take this solute and you pour this solvent in and it dissolves and it's room temperature, that's a terrible solvent for recrystallization for that solute, because it just dissolved your crap away. Like, oh my God, what were we gonna do? I should have said that. But it's just gonna dissolve your solute away and you'll never get it back. How is it gonna crystallize at room temperature if your solute is so soluble in your solvent that it solubilizes at room temperature? Remember, at the end of this experiment, which I'll show you, your solute should not dissolve in your solvent at room temperature, only at boiling. When you induce more energy into that solvent and you create a rolling boil, then your solute should dissolve, but not in ice, not in cold temperature, and not at room temperature. That's very important. So it's not just about polarity or non-polarity, it's also about temperature at hot, cold, and room temperature, standard room temp. Very important for solvents to be able to meet all of that criteria for recrystallization. And also, now, to tie all this together, there's another really important factor that has to go with your impurities. Your solvent should dissolve or solubilize all of your solutes at all of your solutes impurities, at all temperatures, hot, cold, and warm. We are going to solubilize the impurities with the solutes in room temp. It would be good for them to go away at that point. If not, then when they're boiling, the impurities should solubilize there. At the very end, when you vacuum out all of the solvent from your solute, you're going to put a little bit of ice cold ethanol on top to wash away any of the impurities that might have been in the surrounding solution, and they're going to wash down into the filter flask. So you have to make sure that your solvent solubilizes the impurities at room temp, hot, cold. Very important. The more of that impurity that's solubilized out of the crystal, the more pure the recrystallization experiment, the more pure the crystal is going to be at the very, very end. You might notice that I'm stuttering a little bit. I'm trying very hard not to use the word crystallization or precipitation because we're actually doing recrystallization, and I want to keep that clear in your head. But a crystal is a crystal. It doesn't necessarily mean that we're crystallizing it. It's just what you get back. But remember, we are doing recrystallization, not crystallization, not precipitation. No. Last note that I want to mention, polar compounds, such as a compound containing any one of those functional groups, or those little chemical branches for now, in case you aren't familiar with what a functional group is, they are able to dissolve polar solvents. And likewise, nonpolar compounds tend to dissolve nonpolar organic solvents like benzene, hexane, ethers, whatever. But it's still important that your solvent is not so high in its solvency, or that it will not super dissolve your solute or your solid in itself. If it does, you won't be able to retrieve it back. You might be able to take a solute that was solubilized in, for example, diethyl ether, right? And now it's got this diethyl ether that has a super low boiling point, like what, 33C, something like that. You put that on a hot plate and you can vaporize away all of your ether. And what's left would actually not be a crystal. It would be a precipitate, because you're precipitating that stuff back out. So you can save a solute like that if you should put it into something that's super, super volatile. But what if you put it in water? What if your water is your solvent and it has a high solvency? Now you got to boil your water and try and vaporize all that away. And the issue with that is going to be that as you're boiling your water away, some of the molecules of the solutes are going to go with it, and your net yield is going to be super, 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 super low, your percent recovery. So those are important things to remember for solvent requirements. And I told you I would show you this. It's a solvent polarity chart. You see an arrow going this way, you see an arrow going that way. Less polar solvents are more to the left, more polar solvents are more to the right. Far right are the most polar, and the far left are the most nonpolar, and the ones kind of in the middle are the ones that are a little bit polar or nonpolar both. So this is an important chart when you're trying to figure out, well, is this solvent polar or nonpolar, or is it something in the middle? Just go to this chart, it answers your question. Say I give you on an assessment something, they're like, oh, well, that thing that I'm looking at is totally polar and nonpolar. So I would probably want to use a solvent in the middle. Well, I wonder what solvents I could use. Oh, look, methylene chloride, or whatever this tetrahydrofuran is, or ethyl ether. Oh, maybe those are ones. Are they on the selection? Are they on the list? Oh, look, they are. So this is where you want to look for polarity solvent indexes, but also Pavia gives you one that's really, really good. Interestingly enough, I think Pavia puts methanol somewhere in the middle of polar or nonpolar, and this chart kind of puts it all the way at the polar section, but it's still not totally polar. Methanol has characteristics that make it nonpolar too. That's why it was able to solubilize some of the cholesterol that we were looking at in our solubility lecture from week 1. So it's important to remember too. Volatility as it pertains to recrystallization. We kind of already talked about this, just to bring your attention to this little apparatus on the right. That is actually a dry oven. A dry oven is used in order to bake solvents out, of a crystal. So if you have a solvent like ethanol and you saturate it inside your solute, you vacuum that away, and hopefully all that ethanol dries out. But if it's not dry enough, take that crystal, put it on a watch glass, and pop it into the oven for a couple of minutes, and that solvent will vaporize away. Don't leave it in too long, especially if that heat is too high. It's actually going to melt your crystal too and probably vaporize that away. So you got to be careful with dry ovens. But a dry oven is a way to dry out a volatile crystal from a volatile solvent from a recrystallized product. And volatile solvents determine the ease by which the solvent can be removed. The more volatile the solvent, the easier it is to take out of the crystal. But again, more is not necessarily better. You want to make sure that the volatility is not so much like acetone, that your solvent may not even, it could probably boil at a very low temperature on the hot plate and boil all away. And then you're just precipitating your crystal over and over and over again. So volatility is something you got to consider when you're selecting a solvent too. And volatile solvents are dried easily, and care must be taken to place the crystal in a dry oven setting that's lower than the melting point of the crystal, but it's also hot enough to vaporize your solvent away. You need to make sure that that actually happens too. Just as a definition, a flash point, because you might see this in your SDSs that you research, flash point is the lowest temperature by which a volatile solvent will evaporate and mix and combust with air and then continue to result in a flame once the heat source is removed. That is what a flash point is, just for your reference. It has to do with the solvent. We don't really talk about it too much, but if you're seeing it on an SDS, you're not sure what it is, that is actually what it is. As solvents with high boiling points should be avoided to prevent vaporization of the solute. That's very important. So yes, volatility is important when choosing a solvent. Something super volatile like diethyl ether is probably going to be a really poor choice to recrystallize a compound because it has the potential, as I said before, to vaporize away certain parts of your organic structure, and therefore, if your solvent's vaporizing away and it's taking your solute with it, your net yield or your percent recovery is going to be artificially too low. It's going to be much, much lower. And you'll get an opportunity to see data like that next week. So, additional weight of solvent will weigh the crystal and increase the percent yield over 100. Say I'm supposed to get back like 5 grams of this stuff that I'm recrystallizing and I get 4.5 back. That's not really that bad. You can do the percent recovery calculation to figure out how much net crystal you actually recovered from the experiment. But if I take a solvent that is really not volatile like water and I use it to recrystallize, and I don't take all that water out by means of drying, perhaps over a week sometimes, your crystal might get you a recovery of, say, 102% or 105 or something similar. In that case, there's 2 reasons why data will be artificially too high when it comes to percent yield. Either you did not dry out the solvent enough, and therefore it is weighing also because solvents have mass too. It's being calculated or factored into the final weight of your crystal, or it could be that you did not do a good job in the recrystallization process and actually had impurities that stayed into the crystal, and therefore now those impurities also have weight and are adding to the mass of the crystal, and therefore your percent recovery is coming out to higher than 103%. It's very unlikely that your percent recovery will be anything close to 100. And if it is, it should actually be worrisome because there is always a loss in recrystallization. There's actually an equation that you can use to calculate how much of the loss you might predict to get. This is not what we do in this lab. However, it's important to know. It's actually in the Pavia textbook if you'd like to look it up. And it's important to know that just in general, solvent impurities add mass. If you see a number over 100, you're probably looking at an impurity. And if you should have precipitated your crystal instead of recrystallized it, that is most likely why you would see, again, a solvent over 100% recovery. So all of those 3 things are important to talk about if you should ever get data with a recrystallized product that is higher than 100%. There should always be a net loss. You should never recover 100 back. It's just a technical error for everyone that exists. This technical error exists for everybody, and it's almost like pretty understood that you won't get 100 back, okay? And that's just have to do with skill, technical skill, but also even like the glassware that you use to recover something. If the graduations are good and you're doing a good job measuring, that's okay. If you're kind of estimating or eyeballing, which you don't want to do too much, but you can because this class is not quantitative, it's qualitative, you could do that, but you also realize that your yield is going to be a little bit affected, and that's okay because this class, again, is qualitative, not quantitative. So we're not in quantitative chemistry anymore, thank goodness. Recrystallization of a solid. You can have 2 means to remove a solvent from a solute: gravity filtration and vacuum filtration. And you might have to use both, or you might just use one or the other. If you boil your solute in a solvent and you're ready to, and you see like solid chunks of black stuff or blue stuff, or brown stuff, whatever, you want to get that stuff out because it obviously didn't solubilize like your compound did. So you would take a gravity filtration where you take a funnel, you put a piece of filter paper and a beaker, and you put the hot solvent in and it all runs down and it collects the solids on top and your solvent comes out on the bottom. You take that, you let it cool at room temperature, it starts to grow a crystal. You take that after it's warm, it's cool to the touch, and you put that on ice, and then you get the rest of the crystal yield out. That is what gravity filtration is for. If there's nothing solid left over after the rolling boil of your solvent, you can use a vacuum filtration. And the vacuum filtration, you just set up your vacuum flask, you connect it to a hose into the vacuum line, you turn it on, and you put your solvent right through the filtration filter pad. It goes down, the impurities and all the dirty stuff go on the bottom, and your crystal that's solid should remain on the top. You continue to allow that vacuum so that it tries to suck out all of the solvent that it possibly can to get your crystal as dry as it can be. That normally takes about 15 minutes. And then once that's done, if the solid looks good, you can do melting point on it right away and take a weight. If it looks a little wet or saturated, just run it for another 5 minutes. And if that doesn't work, talk to your professor, because you could probably put it in the dry oven and just save yourself more time vacuum filtering the solvent away. At that point, if you take that crystal and you did a good job, that crystal that you now have should be pure. If there's any particulates, you would have to recrystallize that again. Make sure you do a gravity filtration this time and then do a vacuum filtration. So it just depends. If your impurities are not soluble at high temperatures, gravity filtration is the way to go. If they are, then you can skip gravity filtration and go right to vacuum filtration. Again, if you're not sure, ask your professor. I'd like you to take a moment to kind of just think of this picture. I'd like for you to stop and just kind of think about what we've talked about in lab, what you've read in the or watched in the instructional videos and in the instructional information, and see if you can put together a step-by-step procedure for this diagram for recrystallization. So pause this video now and try and get your best guess as to what's happening in this illustration, and then I'll go through it with you. Okay, so now we're ready to talk about what you have. For step one, all the way to the left, you have a solid, and you're going to add the solvent. That's what that little beaker is showing. And then step two, you're going to add that solvent that you chose to the solute, and you're going to take that, and you're going to add heat. That heat is going to dissolve totally your solid, and you are going to then have a solid or a solute solubilized in a solvent. You take that out and let it go to room temperature for step 4. Once that goes to room temperature for step 4, the next thing that you can do is to separate out the solid, the new crystal solid, from the solvent that you have by some means of filtration, or you can just let it evaporate. This step is a little bit more lengthy than we would normally do in lab, because since they chose that method, now we have to solubilize the rest of the crystal solvent in another type of solute. If you look at the step, which should be 5, you see these little red dot things. These little red dot things are kind of what you're looking for, I guess. That's the way I interpret it. And this yellow stuff is probably the stuff that you likely don't want to have. So now we need to separate the yellow stuff from the red stuff. And you notice that the red things are not in step 1. So now that they're prevalent, you get a lot of impurities going away, and you can kind of see, I guess, this red thing that you're looking for. So you add more solvent, again you add heat, you solubilize more of that yellow junk into the solvent, and now we're going to use gravity filtration in order to take out the step that I guess we're trying to collect, which are those little red things. You take that solvent, allow it to cool at room temperature, and slowly more of those crystal seeds are going to form. That'll be your second crop. You isolate that crop from the yellow solution, and then you have more of your crops of crystals. And I would actually keep these 2 crops of crystals separate. Keep the ones in this filter separate from these, just in case these happen to be more pure because they've gone through recrystallization over time, a little bit more than the first crop were. You can test them, and if the melting points are sharp for both, then you know they're both pure. And if they're sharp for this one and not for this one, then you know these are more pure. So all in all, if you were able to figure out the solvents and the temperatures both high and low, remember, step 2 shows a high temperature. Step 3 is the cooling process, which is why it shows a low temperature. That's the most important part of what I wanted you to gather from this diagram. So if you were able to get at least that much, you are on the right track. If you didn't, go back and watch the instructional videos, especially the ones that show the diagram of the crystal being cooled over time or cooled rapidly, so that you can see the difference of why time is so important when you're trying to recrystallize a solute. Remember, you go low and slow on the hot plate, and then you go warm from room temperature to cold ice. And the ice is only used in order to induce the last bit amount of crystal seeding that you might get in order to increase your yield a little bit more. It's not to trap or ice shock. That's why you cannot go from hot water, hot solvent, to ice. You have to go slow over time. As long as you're doing that, you're going low and slow, you are recrystallizing and not precipitating. Okay? So there's one troubleshooting that I want to talk to you about, and it's called oiling out. Oiling out is what happens when a solution does not recrystallize a solute, and rather it just turns it into oil. And you can actually see this thing in the middle? You have this white cloudy thing and this clear thing, and over here you have the same thing. That's called oiling out. You have like a polar or nonpolar thing happening, and the oil is just kind of floating on top, and you don't want that. So if you should get that, and some of you might, you want to scratch with a glass stir bar against the glass beaker. That is called seeding. So as you're scratching the glass stirring rod onto the glass beaker, all these little glass fragments are stirring into the solution, and they're not going to melt because obviously it's glass. It's not going to melt no matter how good it gets. And the crystals can then look at these little glass seeds, what they call, surrounding in the solvent, and they start to trap, and they start to grow and seed their scaffold around this glass. And that is what's called seeding, and that is how you would troubleshoot something that you get with if you should experience oiling out during your recrystallization. You seed the oil in the original mixture, and that will start to cool, and the solution will start, the crystal will start to grow a scaffold around that glass. You can also take a little bit of ice, and some people use dry ice, but for now, at this moment, we don't have dry ice in our labs. Put a little bit inside there, so long as it doesn't react with your solvent. You should ask. If it's ethanol, 95% water, it is okay to do that. Put a little bit of ice crumbs in there, and it should induce a little more crystallization, and that will help you troubleshoot your oiling out. And finally, we're going to talk about decolorization. Decolorization is done with charcoal. Some of you might have seen black water. It's a type of water that's specific to people who think that you can drink charcoal water and that you're actually cleaning out your intestines and whatever. That's not really, well, I don't want to say it's not a real thing, but it's something that you might see on the market. You also have people who put it on their mask and they try to use charcoal to get all the impurities out of their pores. In our case, we use charcoal, just the same, black charcoal, and we add it to hot solutions when we see a lot of color. So if you have an unknown that happens to be like really vibrant, violet, purplish color, you add charcoal to the solution. And what the charcoal does is it looks for all these impurities and it sucks it up into the charcoal. And then once you do that, you go to your hot filtration, filter out the black charcoal, and the solution that comes out will be clear and colorless. And that's because the charcoal just took up all the impurity junk around the solution. So by that means, decolorization is the usage of charcoal in order to remove impurities. But remember, you got to remove the charcoal before you can start to recrystallize. Otherwise, you have to boil it all down because it will crystallize in the charcoal, your solute. But you want to make sure that it's hot and that crystal is completely solubilized in the solvent. So when you're putting it through the gravity filter, the only thing that's staying on top is the charcoal and the impurities that it's sucked out. And what's coming out on the bottom is your pure, hot solvent with your hot solubilized crystal. And then you put it on the counter, let it build to room temperature. It will start to seed and to scaffold. If it doesn't, agitate your glass stir bar on the bottom of the glass beaker. Get the seeding to induce. You can try to put a little ice if you have to. If you're using ethanol, that's totally okay. Don't use too much. Don't use too much. Less is better. And you take that, put it into an ice bath, your beaker, get the rest of the seeds going and get the yield up high as you can, and then put that onto your vacuum filter. Separate out the impurities with the solvent. Take your crystal cake, dry it. If you see any color or anything that looks a little bit, like abnormal, like, oh, it looks like a little brown thing there, take some ice cold ethanol with a medicine dropper, drop that onto the filtered cake and try and wash the impurities down to make sure that there's nothing on the surface of the crystal. Wash those impurities back down, and then you can take your crystal, dry it, run melting point, try to identify what it is, or at least confirm, if you already know it's sulfanillamide, what it is. And if you are using sulfanillamide, the impurity at this point, that bright yellow stuff, which happens to be fluorinone, that stuff is going to solubilize into the solvent, and you can tell, like, oh yeah, this impurity really solubilized in the solvent. I can see it. So if there's any yellow still left on the white filter, on the white crystal cake, you need to do a little bit more washing to get rid of the last of those impurities. If you don't see any more yellow on your sulfanillamide, then you're good to go, and you can start just drying and try and get your melting point to identify that this thing that you actually recrystallize back is pure sulfanillamide. If you don't know what your thing is, just make sure it should be clear and colorless. If it's an unknown, just to make sure that's standard across the board. If you have any questions, ask your professor. Don't just go by faith. Ask your professor and make sure that your observation is correct. Whether or not you think that this compound now can go into testing, especially if it's an unknown. And once you get that data, you'll run mixed melting point with the standard or with the unknown that you have, and you'll try to identify it that way. And remember, it's very important that you're sure and confident that your crystal is recrystallized appropriately and that it is pure. If it is impure, the melting point will be drastically different, and you will not be able to identify your unknown.